So, welcome back once again, and as promised we would start discussing the notion of tangent cones today. In the last class, if we go back to what I have said, then you would observe that we ended up with this sort of Karush-Kuntaka necessary and sufficient condition. I have proved the necessary part, and you can prove the sufficient part yourself by employing the definitions of convexity of f and g and the affineness of this class of constraints A x equal to b. So, we have said that a major role here has been played by an object called closure of the cone of a convex set translated to a point x bar. So, basically what happens is that sort of cone has a particular geometric structure, the closure of the cone of. So, if you take a convex hull of C, we saw that this cone had played an important role. Actually, you take any set C, a convex set like this, and you want to generate a cone, that is, take any element and take every element of C and pass rays through the origin through those points. So, basically at the end you would end up with something like this. So, if this set is closed, then of course, you will have, for example, if this king point is not on the convex set C, then the resulting cone will not be closed. So, this is what is the cone or maybe cone generated by the set C. C minus x bar means you have taken a point x bar and then you are doing C minus x bar. So, 0 becomes a part of the cone. Basically, you translate the cone, what the position of x bar is now taken up by the point 0. So, origin becomes a part of this. So, you make this translation C minus x bar, where x bar is some element here. This particular cone or the particular cone that you will now see coming out of this has, for a convex set, has some meaning. For example, if it is C minus x bar, where x bar is not in the inside, but it is in one of the boundaries like here, then you would actually get a cone like this, sorry, you get a set like this. This is your C minus x bar, and then at the point 0 you are trying to draw some sort of closed convex cone. So, now this has linked with the notion of the tangent cone or the Bouligand tangent cone, Bouligand contingent cone. So, it was discovered in 1938 by introduced in 1938 by Bouligand for a very different purpose, not for optimization, but it has certainly come to play a important role in optimization. So, if you look at the very basic notion of a tangent, which you have learned in high school, is that if you have a curve like this on the Cartesian plane, then you take 2 points P and Q, and if you want to draw a tangent to this curve at P. So, tangent is a line that touches the curve only at the point P, the tangent at P, and does not touch at any other point. So, what you essentially do is you join these chords P Q and then take this succession of points coming towards P. So, you basically then start joining P with those succession of points, and finally, you end up with a line like this. That is your limit. So, that is your tangent. Now, this is the tangent to a curve. What about the tangent to a convex set? So, what do you mean by tangent to a convex set? So, in this case, the notion of tangency, here you see, here you are talking about a smooth movement from Q to P, but what about if the set is discrete, or means just some few points? Can you talk about a tangent to it? Of course, here we are considering convex sets, we need not bother about all those things. So, if you look at this picture once again of this c minus x bar, and I am trying to draw a cone generated by this c minus x bar, if you see all these lines are some sort of tangents. So, the tangent cone to c at x bar, so consider a convex set C. And then V element of R n is a tangent to C at x bar if there exists a sequence. This symbol is a short form for the word there exists. A sequence Vk of vectors going to V and lambda k, which is real numbers going down to 0, that is they are all positive going down to 0, such that x bar plus lambda k V k. So, any vector V which satisfies this property would be called a tangent to the set C at x bar. Now, observe that here this, when I am having a real sequence, my sequencing, that is my indexing, is on the bottom, and when I am talking about a vector sequence here, my indexing is at on the top. So, this can have an equivalent definition that a vector V element of R n is tangent if there exists x k, sequence x k converging to x bar and lambda k converging to 0, such that x k minus x bar by lambda k converges to V. See, this also comes from this fact, when both of these are equivalent, you can check it out. If you look at this diagram, the idea is actually built in here, the tangent to a curve, that when the difference, when x k, the sequence is coming to x bar. So, if this is x bar, the sequence is coming down to x bar, then there would be a lambda k which controls it. So, it does not just become this, thus vector does not become 0, but it is controlled. So, its direction, it is controlled by lambda k in such a way that ultimately the limit of these vectors are pointing in a certain direction. So, if you have a tangent, if you have any set here, I will assume that this set, for example, this nice looking convex set C. So, then what is the tangent? Of course, there are two curves. So, you draw these two curves, but I can talk about any sequence coming to this point in C. So, what is important is this x k must be in C, and I am looking at these differences x k minus x bar, x k minus x bar, and then modulating it with lambda. So, these vectors that will be generated by other sequences in C, they can be now thought of as a tangent vector, may not necessarily be thought of as a tangent vector. Those who are more akin, more habituated with the school geometry or coordinate geometry might be having a little bit of problem, but let me tell you that in convex geometry or the geometry of optimization, everything is one sided, because convexity is one sided, because you use an inequality, and as a result of which your geometry is not both sided like the tangent here, your geometry here is also one sided. So, this, if you look at it, I can call the set of all these vectors, they form a cone, and that is called the tangent cone to V at x bar, to C at x bar, the tangent cone. And so, set of all V's form this set which is called, which is a cone, and which we call the tangent cone. Now, when C is convex, this can be defined for any set C, but here we are gluing ourselves to a convex set, because essentially we are talking about convex optimization. So, rather than complicating the facts of life, it is essential that we just concentrate on the things at hand, the things that we really are interested in, that is of minimizing a convex function over a convex set. Now, if you look at this thing, the question is, and if you see the pictures that we have drawn of tangents, this tangent here, this can be proved that try this as homework, or I will show it to you tomorrow. So, if C is a convex set, the tangent cone has a beautiful and clear expression. So, what is this tangent cone useful for? That is the first question. So, a tangent cone is useful possibly in using its for its use in optimality condition. Now, you might say that okay, how many optimality conditions you are going to use, because you know optimality conditions we have been studying from the beginning, but you know optimization largely is story of finding optimality conditions that would lead you to compute the points. Now, you have already seen the normal cone. Of course, the tangent cone has some relationship with the normal cone, and the optimality conditions gets redressed as you change from normal to tangent cone. If we go back to our story, you will see that with the normal cone, the subdifferential is involved, or the subdifferential itself is involved with the normal cone. 0 belongs to del f x naught plus the normal cone, or 0 element of grad f x plus normal cone. The directional derivative is associated with the tangent cone. So, the tangent cone geometry is expressed with the directional derivative, and the normal cone geometry is expressed with the gradient or the subdifferential itself. So, there is some sort of duality between these two things, normal cone and tangent cone. So, the duality involved in these expressions is also expressed by the tangent cone and normal cone, and these dual relations will come very soon, but let us see what the tangent cone can do. Now, there is another interesting way to look at the tangents, the notion of tangency. How can you arrive at such a notion of tangency? So, we are studying optimization. So, we are essentially talking about variation, that is, if I want to say that some x bar is actually a minima, then I should be able to say how it is varying with respect to other points. That is, if I am having a point x bar here and I want to say that this is a minimum, then if I move a bit away from x bar and still be in C, say I have this direction w, and this new point is x bar plus some lambda w. If this is a minimum, I should always, for a function f, I guess, then this must always be true. Now, the important thing is that the direction that I am choosing has to be of this form, that x bar plus lambda w must be in the set C. So, lambda of w must be in the set C minus x bar. Say I take lambda to be positive, of course, I am moving along this direction. So, it is positive. So, because lambda is positive, this is element of 1 by lambda times. So, this simply says that w is element of closure of the cone of course, in the cone and hence in the closure. So, any W for which I can measure this change, this variation, that is f of x bar plus lambda W minus f x bar. I am measuring this variation. So, if x bar is the minimum, so moving along those directions which will keep these new points, these points in the set C would actually should give me this difference to be greater than equal to 0. So, this is the variation that we are trying to measure. So, but over which points, along which directions I should measure the variations, those directions should belong to the tangent cone. So, the very notion of variation, which is very fundamental to optimization, that is the very basic definition of what you mean by an optima, is intimately linked with the notion of tangent cone. And hence, it is important that we have some time to see how this idea is linked with optimization, in the sense that how it is linked with optimality conditions. Now, suppose I have chosen this W over this for this convex function, this W from the tangent, and then what I am having is that if x bar is a minima, then actually if you observe, I can remove this by x minus x bar, I can take any x here and do x minus x bar, and if I move along those directions x minus x bar or lambda x minus x bar, this will be actually true. So, what would happen if I apply differentiability property of this? I will simply get so this is my optimality condition, and in fact, if the function f is not differentiable, then the directional derivative in the direction x bar in the at the point x bar in the direction W must be greater than 0 for every W. Now, this is a very important fact that you must note. This is an important fact. So, here you see how the tangent cone is playing a role. Then what is its link with the normal cone? So, are we having two different optimality conditions? Can we move from one of these to the other? Can we from here, can I come from here to this condition? And if this or this replaced with the subdifferential. So, can I come to such conditions? See, this thing would require some more tours into the land of convex analysis. Convexity is so fundamental, but so intrinsically beautiful that never mind, even if you are engineers who are in the audience, or maybe people from management sciences who just want to plug in and get the answer and declare a non-optimal point as an optimal one, can also take some pleasure from the beauty of this subject. I would like to emphasize that when I say that you are pushing a button and telling a non-optimal point as optimal, it is not with an intention to ridicule anyone. The intention is clear that most people who practice optimization, at least in India, in my country, hardly really know the mathematics behind optimization, and unless you are aware of the mathematics behind optimization, it is not really possible to appreciate or really know what algorithm to use on what sort of problem and when I would stop an algorithm. See, it is very important to know at the very outset, because what happens is that you would just have a problem, you would have some MATLAB, F mean con something, you will put in your problem and they will throw an answer and you would accept it. and possibly declare it as your solution in optimal point. The very important fact that you should learn when you study optimization, and I want to stress it again, if you read Yuri Nesterov's book Introductory Lectures on Convex Optimization, this is what he writes in the very beginning, that optimization problems in general are not solvable. Of course, you can solve toy problems like minimizing x square over whole r, or minimizing f x equal to x when x is in r between -1 and +1. These are toy problems, but real problems. When I am talking about optimization problems, I am talking about real problems. Say quadratic optimization problem, you just can't solve it. If a real quadratic optimization problem with a large number of variables, large number of constraints is not so easy to do. You just can't solve it. Even if it is a convex problem, what you get is an approximate answer, unless there are very special structures or very special situation. So, they are not solvable in general. Then what is the need to study optimization? Am I not to find the actual minimum? Then how do I solve my problem? You say minimize this, and you just say that, oh, you can't find the minimizer. So, why are you wasting all this time speaking about optimality condition, etc. Theory, by the way, is always naive in the sense that there are a lot of assumptions. We assume the perfect world for a perfect theory, but the real world is not so perfect. So, your theory is only a guiding tool to tell you how good is the approximation that you have taken. So, what you take at the end of running algorithms is an approximation. How good is your approximation is what theory will tell you. How does your point satisfy the Karush-Kuntakar condition at least, or how far is it from the Karush-Kuntakar actual Karush-Kuntakar solution. So, these are the things which makes learning of the theory important, whether you are engineer or in management science or something else, or of course, for mathematics or you are in computer science. So, we will come into algorithms very soon, I will not say very soon, but maybe in few more lectures, but we will give an extensive time on algorithms. But it is very important to understand at the very outset that theory is always guiding you to generate those algorithms. Now, once I have done this, let us see. So, in order that you go back and forth between two different types of optimality conditions, one expressed in terms of tangent cone and directional derivative, another expressed in terms of the gradient or the subdifferential and the normal cone, you need to know a bit about the notion of a polar cone. So, let K be a closed convex cone. I do not need a closed convex cone to give a general definition of a polar, but our cones are essentially closed and convex in most cases. So, we just assume that fact. Then the polar of K set of all x in Rn such that x times w is less than equal to 0 for all w in K. So, if that is my definition, let me take the simplest example R2 plus. So, take any w in K, R2 plus, take any w here. I want all those vectors v which will make an obtuse angle with this, that is, the angle has to be more than 90 degrees. So, the all points here will, all the vectors here in this third quadrant will form an obtuse angle. If you take some vector here, it will form an acute angle, any vector here will form an acute angle. So, essentially if I write R2 plus the positive orthant, non-negative orthant, and take its polar, it is nothing but the minus of R2 plus. Suppose you take any cone like this, so you have to find points which will make obtuse angle, it cannot make acute angle. You take any point here, it is making obtuse angle. Take any point here, it is making obtuse angle. Here again for this particular cone, where I have halved the, I have just drawn a line and rubbed the other part, it is still again minus R2 plus. So, if you take this as k, then this is again k polar. Then I must just look and ask this question, what is the polar of the polar? That is just a curious question, nothing much to worry about. So, if I define it, this consists all W in Rn such that W times x is less than or equal to 0 for all x in k polar. That is the definition. I am just repeating the definition, removing k with k polar, that is all. That means that I am asking the question, what is this? The interesting fact is that k polar is equal to k. K polar is equal to k. That is the interesting thing. So, how do you do the proof? The proof needs separation theorem. So, try this as homework. Tomorrow I am almost going to take an assignment class by trying to show that the tangent cone is that, and also try to prove this one. Now, why am I telling you all this story of polar and all these things? Does it have any relationship with our subject at hand, tangent cone, normal cones and optimization? The interesting fact is this: if you take the polar of the tangent cone, you come up with the normal cone. That isn't that fascinating, that you just the geometry, you just have to look into the geometry. So, these two things are so geometrically linked, that this is a set of all vectors v which makes obtuse angle with elements of the tangent cone. And now, you take the normal cone, you take the polar of this, which is polar of the closed and convex cone T c x bar. So, you take the polar of the polar, and then by using this thing we get this is nothing but the tangent cone. This is quite interesting, but now my question would be, how do I get back between two optimality conditions? For that we really have to wait a bit. Now, once we have discussed all these optimality conditions, this sort of geometry that is involved in the whole discussion, let us get a bit bold and look into the structure of the convex functions still more in more detail. You look at a convex function, you see you look at this epigraph basically, APF. Now, you have at every point of this closed convex set, because I have drawn a continuous convex, nice looking convex function, and so it is finite valued. So, it is continuous, and so at every point you are having a tangent hyperplane, a supporting hyperplane, and you see what are these supporting hyperplanes. The supporting hyperplanes are defined by affine functions. So, basically you take any affine function which is lying below the graph of the convex function, and then take some sort of a upper envelope of those collection of affine functions. They would actually generate you the epigraph itself, the convex function itself. They will generate you the curve, the graph of the function. So, what happens is that take a convex function f, this is f, and then take affine functions of this form such that f of x is equal to, is greater than equal to h x for all x. So, here we are talking about affine functions, we are not talking about something vertical, we are not talking about a line like this which talks about the affine function x equal to 0, right. In the R2 space it is the affine function x equal to 0. So, it is 1 0 into x y is equal to 0. So, we are not talking about these sort of I am not talking about a line which just gives you x equal to 0. I am talking about non-vertical hyperplanes, because if you have a vertical hyperplane, then it is cutting through the epigraph. So, once you are cutting through the epigraph, it is impossible to make this sort of assertions. So, you cannot cut through the epigraph, you have to be below the epigraph, as a result of which you have to slant down, because if you do not slant down, if you are non-vertical, you cannot maintain this thing. So, you see what I have drawn is all these affine functions has their functional values at any point. You take this affine function, the functional value of f is here, and the functional value of the affine one is here, and the functional value of f is here. So, this is always holding for this class. So, what I am trying to say is that you collect the set of all h which supports this. So, collect all affine h which support this. That set is called support set of f. So, it is a collection of all affine functions h which is majorized by f, or which minorizes f, in the sense that f is always bigger. Now, if you look at now the far reaching result in convex analysis, which actually gives you a global structure of convex functions, is the following. It tells you that a function, if it is a continuous function like this, if f is finite, you always have with h belonging to support of f. So, what do? You take an x and you compute at that x the values of all the h x's which are in this set, and then take the supremum of all those values, and that will exactly give you f x, because you say you take a value here, one of the h x, another h x, another h x, and you go up and you finally reach the graph. So, that is exactly what is the story. So, this is not only talks about the case when f is finite. In fact, if f is extended valued proper and lower semi continuous. I have already told you what lower semi continuous is, lower semi continuous, then this holds. But okay, we are not going to be so much bothered about this lower semi continuous business, because that is essentially a technical thing, but is a very helpful technical thing. But for our studies, we can just be happy with continuous convex functions, because that is more or less the thing that we will handle in practice. This useful device that we had just spoken about, this useful result, has interesting consequences. Now, let us look at this new convex functions, which we construct out of this very idea that if you take the supremum of functions majorized by a convex functions, that you can get back the convex function itself. So, if you take the envelope, upper envelope of a family of affine functions, what you get is a convex function. So, we are going to now define the Fenchel conjugate of a convex function. So, define a function f star which takes any element x star in Rn, x star is in Rn, and you compute the value of this function as follows: take supremum of all x in Rn Now, you see there are two ways to prove that this is a convex function. So, my first job is, okay, of course, f is a convex function. You can prove that f star is convex without even f being convex, but okay, our case is just convex. Now, if you observe this, so what I am having is a family of affine functions. For every fixed x, this is an affine function in x star, and by what we have just seen, the upper envelope would provide us with a convex function. So, this is a convex function, but you can directly try compute it. So, f star is a convex function. One must be wondering why all this operations. Now, there is something interesting about this operation. Let me look at f star 0. Its supremum x star is 0. So, it is 0, I do not use this. So, this means the negative of the infimum of f x over R n. So, this is a very fundamental fact, which means that if I have a finite infimum, then f star is a proper function. See, f star can never take the value infinity, because if f is a finite convex function which we are taking, then you put any x star, then there will be for given x, these values are always finite. So, it will never take, the supremum cannot be minus infinity, because R n anyway is not non-empty. So, The supremum could be plus infinity, it could blow up the supremum. So, if the function f has a finite infimum, then you are guaranteed that this is a proper function. There will be at least one point which is 0 where the function is finite. But it can be proved that if you have a convex, if you have a finite function f, it would be anyway a proper function. So, this f star is actually an extended valued function. But since f is finite, there exists at least one point where you have f star finite. So, f is a nice coercive function, nice function which has a minimum over say x square, then f star 0 is 0. Okay. We will try to find the usefulness of this, and in fact, tomorrow we will come with a repertoire of examples of f and f star and its implications of in optimization. And this function has brought in a new area called computational convex analysis, which is a thriving area which one might get interested, somebody in mathematics might just get interested by this whole thing, or somebody who wants to work in the interface of math and its associated computations. So, if you look at this, I am yet to give examples, I am not going to give examples today for this particular case f and f star pair. So, if you observe f star x by very definition is bigger than x star x minus f x for any x in R n. This would imply f star x star plus f of x is bigger than x star x. So, this is called the Young-Fenchel inequality. You might think that there is no use giving this such a triviality a name, because it is just obvious from this definition. Yeah, it is obvious, but what is not so obvious is the fact that equality holds that is f star x star plus f of x is x star of x if and only if x star belongs to the subdifferential of f at x. So, if f is differentiable, then x star is exactly equal to the gradient of f at x. So, with this very basic introduction to the notion of conjugates, conjugates play a very important role, because when I had defined a convex function f, a convex minimization problem or minimizing a convex function over a convex set, there is some other convex problem which is defined, or rather concave problem which is defined in terms of the negative of f star, which is called the dual problem, which comes into play, which we will soon talk about a little later. And then this is exactly a very basic thing what we have done. So, tomorrow we are going to give examples, and we are going to prove what we had said, that we are going to prove k naught naught is k, and let us see what we had given you in the homework. We have given you to prove this one. So, this is what the tangent cone, when C is convex, this is what the tangent cone is. It follows from this definition, would give you into this definition, and of course, we are going to prove this fact. But before we do so, we would give a repertoire of examples from of a pair of f and f star. But now the question is, what would happen if f is not just finite, it is extended valued but proper, that it is finite at least one point. So, then can you define this? The answer is yes, you can define it in a similar way, and you can show that when f is proper, that it has at least one finite value and it is never taking the minus infinity value, then f star is also a proper function. Because once we, for example, the interesting question, what happens if this is the indicator function of the set C, then what is the f star? So, we will try to figure out those things and they are pretty interesting. So, and has lot of linkages with optimality condition that we also figure out tomorrow. So, with this we end today's talk. Thank you very much.